All right, we're ready to start the last talk of the day. The speaker is Ines Aniceto, from asymptotics to exact results in string and gauge theories.
Well, thank you, and thank you, the organizers, for letting me speak and present my most recent work on this subject. I have to say that I was expecting to get a bit of the heat wave from Europe after coming from the UK and having several weeks of rain already. So why can't the organizers get more warmth? So I will be talking about my work on asymptotics and how can you get actually exact results from asymptotic behavior in perturbation theory. We have many different techniques to learn about systems and observables in physics, but in order to compute explicitly many observables, we still rely a lot on perturbation theory, hoping that it will still give us some hints of the analytic behavior of our observables. And this is true from energies in quantum mechanics until large N expansions in gauge theories. But it does happen that often these expansions are actually divergent. So if we calculate a few terms, we get a very good result. But if we calculate more terms in our expansion, we get a much worse result. And basically that means that they're asymptotic. But it is well known that this behavior actually, the fact that we have a divergent asymptotic series when we do perturbation theory, it means that we actually have information hidden in these divergences that is actually tells us about non-perturbative phenomena that exist and govern our observables. What do I mean by govern? So they're exponentially small, so they're transparent in perturbation theory, but if you really want to analyze the global analytic properties of an observable, these non-perturbative phenomena will play a crucial role in that, so you can't just ignore them. So the general goal is actually to obtain global analytic properties of observables. What I mean about analytic properties is that you do a perturbative expansion, you have a local behavior, but I would like to get from that the position of branch cuts, of phase transitions in parameter space. So how can I go from a very localized and, more than that, divergent and asymptotic behavior to actually get a global picture of my observable? So we've been working on many different projects dealing with this. In particular, I will mention a couple that I'm currently doing, which basically are to do with the phase transitions in matrix models, so the analysis of parameter space in matrix models, and also 2D gravity and the relation to Pauli-Witt transcendence. But these systems are actually quite complex, and what I've decided to talk here is about a very specific problem that shows the complexity of the systems that I'm working with, but also allows me to have related some very simple toy models that I can show you how these tools work. And this is going to be basically the late time behavior of strongly coupled systems, which I will explain later on. So the outline of my talk is going to be, basically I will start with a crash course on resurgent asymptotics, where I'm going to put in 10 minutes my physics reports review, or at least I'll give you some hints of the terminology that I will use for the rest of the talk. Also, I will then introduce the actual system that I will talk about, which is some of my recent work on the late time behavior of n=4 super-Young Mills strongly coupled plasma. And the interesting situation here is that actually you can deal with this system via gauge gravity dualities. So string theory will play a role in the analysis of this system. And I will give you a general idea of what the asymptotic analysis gives there. But then I will go to a simpler case, which is the Müller-Israel-Stewart hydrodynamics, where I can actually show you how to obtain some exact results from our asymptotics. And I will then mention the applications that I already mentioned, but with a bit more detail. So first, the primer. So just to have in mind energies in quantum mechanics, this is not accurate. This is just a pictorial idea of what happens. So I want to calculate energies. I want to calculate energies, so for example, the ground state energy with a double well potential, and I want to take my coupling of the potential very small, so I can do perturbation analysis. And if I do that, I get a series in G, for G small. But what happens is that the coefficients in my series, actually, if I take n large enough, so large order, these coefficients start growing factorially. So this series is truly divergent. Moreover, it doesn't only grow factorially, but actually has a subleading exponential growth. And this is well known to exist because of instantons. So this factorial growth is directly related to the fact that we have tunneling effect. Sorry. And that's the non-perturbative effect that is encoded somehow in these coefficients. So, in particular, we don't have just this energy, but we have corrections to this energy, and those corrections are exponentially small, so transparent in perturbation theory, and they come with their own series if you did an expansion around the instanton sectors. So, but basically they're suppressed. So, what's the general picture then? We did perturbation theory, we calculated our series, it's asymptotic. We know that we need to include instanton corrections due to tunneling, and they're exponentially suppressed, but we don't have just one exponential, we have multiple instantons, so we actually have a whole tower of exponentials that we need to correct our series with. Do remember again, so if for computations you would be led to believe that, I want a number, these are very, very small numbers, so why would I want to add them? Again, the idea is to then construct a global picture of my system, and for that, I need to make sure that somehow I have a non-perturbative completion of my observable. And so to add everything, I can do so with what is called a trans series. A trans series is basically a formal expansion in different, what are called transmonomials. So I have here my coupling. It's an expansion in G, but it's also an expansion in my non-perturbative terms, which in this case are exponentials. There can be other transmonomials like logarithms as well. So, and then you can see that I've included here another parameter sigma, and this sigma will actually be extremely important later. But sigma is a parameter that encodes certain like boundary conditions or initial conditions of my system. And this is basically my true non-perturbative completion for the energy. And so one other thing is that each instanton does grow factorially. So all of these series, not just the first one, but all of the series are asymptotic in here. And there comes about the word resurgence, which is basically, so these are all the sectors of the instantons, the different instantons, 0 being the perturbative series, and the coefficients of all the different sectors are related. Somehow, one sector encodes the information about the other sectors. In particular, this is done via large order relations. In particular, if I looked at the growth of my perturbative series, and I really studied very carefully, I would get that factorial growth that makes my series divergent, but then I would get subleading, so n is large order. I would get as coefficients in a 1 over n expansion, the coefficients of the one instanton sector. So somehow, in my perturbative sector, it's already encoded the coefficients of the one instanton sector. Furthermore, if I go deeper into even more exponentially suppressed, I get my 2 instanton sector. And I can continue this further. And actually, asymptotic techniques, in particular resurgence, can give you the exact forms of all of these relations. And basically that means that, so again, the perturbative series encodes all the non-perturbative phenomena. So how do you go about actually seeing that that the perturbative series does indeed encode the non-perturbative phenomena. You do that by doing what is called the Borel transform. What do I mean by this? So I'm going to be very simplistic here, because the Borel transform is basically what you need to do is what's called go to the convolutive model. But again, in simple terms, what I'm going to do, this is all a formal expansion, it's divergent. So what I will do is take an inverse Laplace transform to each one of the terms here. Of course, because I have already divergent series, that doesn't mean that I'm taking an inverse Laplace transform of the full sum, because meaning I'm just doing a formal procedure. And basically what that does actually, it's that it removes the factorial growth. Exactly. And if it removes the factorial growth, what happens is that now you have a series that has a finite radius of convergence. And that finite radius of convergence actually is exactly related to the non-perturbative phenomena. So now I simplified my system. So before, I didn't just have this factorial growth, but I had a whole series. But now let me assume that this is exact, that all the coefficients are given by n factorial divided by over n. Then the Borel transform is just a pole. And the pole is basically exactly where the instanton action is. So if I actually, instead of having just this, I had the full behavior with the one instanton, what I have here, instead of just a pole, is a branch cut. And the information in that branch cut gives us already the information of the one instanton series. So, in summary, the non-perturbative phenomena is directly linked to these singularities that I can find in the S-plane or in the Borel plane. The singularities will be, in general, not just poles, but branch cuts. And just a bit of nomenclature, each directions in this plane that have singularities are called Stokes directions, or Stokes lines. And the structure of singularities can be extremely complex. Here meaning these are actually just poles. This is the large N Chern-Simons on length spaces. This is n equals 2 star supraimils in S4. So this is small G Young mills. So this is just to tell you that the structure of singularities can be quite complex. But one thing that I didn't address, so this tells me that I have a way of grabbing my asymptotic series and digging deeper into the factorial growth and finding my non-perturbative phenomena. But it doesn't tell me how to actually obtain a number from my asymptotic series. And how we do that is basically, so we have a finite radius of convergence in the Borel transform. This is an actual function. And what we can do is basically do the inverse procedure back. To go here, I did an inverse Laplace transform to each one of the terms. I can do a Laplace transform back. And this is called Borel resummation. Of course, many times I don't know the exact form of the Borel transform. I have a finite number of terms and I need to approximate it. I know it's finite radius of convergence and I use methods of Padé approximants, for example, to approximate my function. So this procedure gives me a solution everywhere, almost in the complex plane. I can do analytic continuation everywhere in my parameter space, but there are certain directions where I have a problem in calculating my summation. And these are along the Stokes direction. So along directions where I have a singularity. In that case, I have an ambiguity of where do I choose my contour, above or below my singularity. And what is the difference between those two? The difference, if you calculate just for a pole, for example, it's very easy. It's just residue theorem because it's just a pole. And it gives me exactly this exponential that I had to include in my trans series. If instead of having just a pole I had a branch cut, what would happen is that I would not only get this exponential, but I would get the whole string of the one instanton coefficients. And this is called a non-perturbative ambiguity because obviously this is exponentially suppressed. So Borel resummation, it's straightforward along any direction in my parameter space that does not have singularities. Along the Stokes directions, we have ambiguities. But remember that I said that in my trans series, every single sector was asymptotic. It wasn't just the first one. So all of them will have this problem. But actually, we know from these large order relations, or from asymptotics, how exactly these two summations are related. And do you remember the parameter that I mentioned earlier that I included in the trans series, saying that it's related to initial data or boundary data? And actually what happens across these lines is that this parameter changes by a value, and that value is dependent on my problem, and it's called the Stokes constant. It's numeric, and in our case, it's imaginary. And basically, what happens is that, so even though each one of the sectors will have an ambiguity, what I can guarantee is that the whole trans series, which is my whole non-perturbative completion of my observable, will not have any ambiguity, so that the summation above minus the summation below of the full trans series is actually the same, as long as I fix sigma appropriately, and fixing sigma appropriately means fixing sigma, at least the imaginary part, equals to S over 2 in this case. So, and with that, I have a full analytic continuation all around the complex plane of my parameter. Just, so, one thing that I wanted to say, all around, so I can calculate my function along any direction. The question now is, what is the physics of this summation along different directions? And this is already going towards some exact results. So I've mentioned what happens at the Stokes lines, but at the Stokes lines, these exponentials, the argument of the exponentials is real, and they're extremely exponentially suppressed. Which means that even though the parameter sigma changes and we include all these terms, and they change, the leading term of all these terms changes with sigma, because of the exponentials being so suppressed, physically nothing happens. So there's absolutely no change in our physics. However, imagine that you take a summation across a line where the real part of this argument is 0, so it's only imaginary. Then, right, exactly, it's oscillatory. So then what happens is that these exponentials now will be all of the same order. And what you'll have is actually different physics. So this will hint towards a phase transition. But if you didn't have the full non-perturbative completion of your observable, you would miss this information. Just as a summary before I actually go into the example. So, studying the asymptotics, I know what type of non-perturbative phenomena to expect. I write my completion in form of a trans series. I can sum all the sectors. I can determine my parameter in the trans series from external data or from ambiguity cancellation. And I can do this for any values of G. And then I can study my full result to look for analytic data, the position of poles, of zeros, of branch cuts, anywhere for any values of G. It doesn't have to be for G small anymore. And also the directions of phase transitions in the parameter space. So now I want to go into my example, which is the late time asymptotics of a strongly coupled system. And what I will do is the example that I will do, there'll be a lot of words about the example. So it's relativistic hydrodynamics, which gives us a description of strongly coupled plasmas and a way of having a time evolution of strongly coupled plasmas. In particular, it gives us a description of strongly coupled quark-gluon plasma, like what shows in particle accelerators. But as any hydrodynamics, we have several kinetic parameters that cannot be fixed directly, except if you know the microscopic theory that is behind the evolution of your theory, you can actually calculate
so what's
this kinetic parameters. And if you constrain your system enough, you can have that microscopic theory can be a field theory. In particular, it can be n equals 4 Superior Mills. Why would I want this particular case? Because in that case I have, if I take n large, so of the SUN gauge group, I have the gauge gravity duality, and I can actually use the dual gravity solution to calculate my time evolution of my plasma. So what is the kinematic regime that allows me to actually do this? So I will use an expanding plasma, and I'll assume that I have longitudinal boost invariance, which is called Bjorken flow. In particular, if you look at the energy momentum tensor, this actually constrains it in such a way that the elements of the energy momentum tensor cannot depend on the spatial directions. They can only depend on proper time. Moreover, if I assume conformal invariance as well, what happens is that I don't have a pressure and an energy, but they're directly related, and I actually have a single function dependent on proper time to determine. So in the strongly coupled super-Yang-Mills boost invariant plasma, all physics is encoded in my energy density. But still, obtaining this energy density is highly complex, so we're going to do one step further and study it in the large proper time expansion limit. Why? So if you're looking at a strongly coupled plasma, at initial times what you'll have is a highly non-equilibrium solution, very oscillatory, very complicated, but there will be at some point a transition to a hydrodynamic regime. At that late times, you'll have the hydrodynamic regime, and that is the one that we want to analyze. So because of conformal invariance, actually the energy density is quite constrained. It depends on the proper time in this way. So basically, the first term, the 1, is the ideal fluid, and all of the extra terms here are dissipative terms. And all the initial conditions of my highly non-equilibrium plasma are actually encoded in just one dimensionful parameter, which is lambda. So, and what I'm going to do is actually now use the dual geometry to calculate these coefficients. So these are basically related to the kinetic parameters that I mentioned that we need to calculate to study hydrodynamic theory. So how does this work? The equilibrium states in my microscopic theory, my CFT, are basically related to solutions, black hole solutions on the gravity side. In particular, because I want flat, meaning I'm interested in a flat metric in my field theory. That means that I don't actually have a black hole, but I have what's called a black brane. And then I can have some perturbative non-equilibrium phenomena, like dissipative phenomena, and that's related to to do linearized perturbations around this black brane solution. This black brane solution corresponds to the ideal fluid, and this to the dissipative terms. But then I have non-hydrodynamic degrees of freedom, which are basically the ones that are directly related to, which are basically exponentially decaying, and they're related to the highly non-equilibrium initial state. And these are related to the quasi-normal modes of the black branes. So just a brief moment that the dual geometry is basically given by a 5-dimensional metric, and we want to solve Einstein equations. So all the metric components can only depend on tau, on the time, and on the 5th coordinate because of the boost invariant plasma, the condition. And basically the holographic map between the two theories tells me that the energy density is related to this component of the metric to the 4th order in this expansion. And the 4th order is because we have a 4-dimensional conformal field theory. So to make a link now with what I said before, I can actually calculate the metric, so do late time expansion in this black brane background, and what I would get is a perturbative solution that is asymptotic. But of course, because I know that there are quasi-normal modes in my black brane, I know that I'll have exponentially decaying modes, and what I do is actually, what I will do is already assume a trans-series solution for my gravity components, and including all possible quasi-normal modes. So basically, I wrote here what the final solution is for the energy density, but as an equivalent expression for the metric ansatz, which we solve. And basically here, we include multi-parameters because there's an infinite number of quasi-normal modes. And these are my perturbative expansions around the exponentially decaying modes. One surprising thing that we found is that typically the quasi-normal modes directly are analyzed. But what we found is that you don't only have the exponentials of minus omega 1 or minus omega 2 here. You can have, for example, coupled quasi-normal modes, omega 1 plus omega 2. And this is directly related to the fact that Einstein equations are not linear equations, but they're non-linear. And all these expansions are asymptotic. So just to give you an idea, again, the Borel plane singularities. So this is for the original hydrodynamic expansion. You have the first quasi-normal modes. Here in red, the second quasi-normal modes. In green, the third quasi-normal modes. And then in purple, what are called the overtones. So the coupling of different quasi-normal modes. Here actually only shows the 2 omega 1 to 3 omega 1, but you can do this for many different sectors, and you can find the relations. So what do we get? We got a non-perturbative description of the late time behavior of the plasma, the super-Yang-Mills plasma. The asymptotic analysis predicted this coupling of quasi-normal modes. And, meaning, we did a gravity calculation where we calculated all these sectors. But we also have these large order relations that predict the non-perturbative, the non-hydrodynamic behavior from the perturbative expansion, and you can compare the two results, and basically this is just a graph of the errors that we of the comparison, and you can see that they're very small, 10 to the minus 54. But can we actually, so this is all late time, this is the trans series, there's a lot of technical details that go into this, but the question now is, can we recover non-equilibrium behavior of early times from my trans series at late times? And how do these trans series parameters depend on these initial conditions? But this is quite complicated for the system, so I'm going to go into a toy model, which is the Mueller-Israel-Stewart. So the setting is pretty much the same. We're assuming boost invariant flow, conformal invariant. We basically now approximate in the energy momentum tensor, the shear stress tensor, by several corrections to the ideal fluid, and we solve the evolution equations for the energy momentum tensor. And what we get actually is an ODE, a non-linear ODE, where this F, it's not exactly, but you can assume that this F is my energy density, and my Z is the large proper time. And these C's are basically the phenomenological parameters that you can set to be equal to the ones of Super-Yang-Mills. So again, we're interested in the late time regime, Z very large. And in this case, this is the Borel transform. We have just one single decaying mode. We don't have an infinite number of them. It's in the positive real axis. It's like the first example that I gave that it was a pole, but now it's a set of cuts. So I can assume a trans series ansatz. It's of the same shape as the original thing that I've shown at the beginning. These are my perturbative series, and this is the action of the non-hydrodynamic modes, or the quasi-normal mode. And this is just the leading behavior of this series. This point is actually the value of A for the C's of Super-Yang-Mills. So at early times, there's a particular solution that is very interesting, which is the attractor solution. It's very interesting because it's a stable solution converged to a finite value at early times, and all the other solutions basically are divergent at early times, but converge very rapidly to the attractor solution. You can actually calculate it as a Taylor expansion in Z, in small z, and you can approximate it or calculate it numerically. So, can we recover this attractor solution from my general solution here of the trans series? And what I want is to fix then the parameter sigma such that I recover that exact solution. So, one of the things is that, again, proper time is positive real. I have singularities in the positive real axis, so I have an ambiguity, which I mentioned at the beginning. So I need to cancel it. And canceling it fixes the imaginary part of sigma. And then I can compare to a particular value of the attractor solution to fix the real part. in this case. So this is what I meant, ambiguity cancellation. I fixed the sigma I to be S over 2. S is pure imaginary. This is the value, meaning I have it with many more decimal cases. So I have the ambiguity cancellation fixing this. So how do I go about using the trans series to compare to a solution at early times? So what I did here is reshuffle my transmonomials of my trans series in a different way. So you can see that here now I have the powers of tau, of z, so of the time, at the beginning, and then the second sum now is my exponentials, where I include sigma, the z2 minus beta, and this exponential to the power n. So this will be a new variable that I call tau, and what I'm going to be interested in is in studying a different regime. It's still late times, so z minus 1 much less than 1, but now it's in a region where this tau, which is this exponential, is going to still be greater than my z minus 1. So this is the smallest transmonomial in my series. And the interesting thing is, unlike the other way, where all the series were asymptotic, this series is not. This is convergent and can be calculated exactly. So basically what I rewrote is this, and now these are my FKs of tau. Tau is this new variable. And I can actually both calculate these AKs directly from my differential equation, but I can also solve the differential equation in terms of these FKs, and this is what I obtain. You can do this exactly. And this is not meaning we can do the same actually for different solutions in Painlevé. So this is something that is true throughout. So actually I get the first one is given by the Lambert W function of tau. And all the other ones are going to be given by the same Lambert W function, but now by polynomials, rational functions of the Lambert W function. And all of these can be calculated exactly. So again, I have my FKs, I've calculated them. I'm in this regime, and I want to choose a Z large enough that I'm still in the late time behavior, but small enough, large enough that it's still here, but small enough that I can compare with my attractor solution. And the easiest way to do that, actually, because the tau depends on the exponentials, is to take Z off the real axis and make so the absolute value of Z will be large because the Zi is large, but still the exponential won't be too small. And basically, I also want to analytically continue the attractor solution to the complex plane. And then comparing the two, I can get tau as a function of Z, and with that, I get my trans series parameter as a function. So I fixed Z to a particular value, and I can get my trans series parameter exactly like this. And this is the result, and I'm basically almost done here. So this is the value that I get with 4 terms here, that are 5 actually, because I calculate tau 0. And I just want to show you the difference. So I know that from ambiguity cancellation that this should be S over 2. And the imaginary part of sigma that I calculate through here, you can see that with 3 terms, it doesn't quite converge. With 4 terms, converges better. With 5 terms, starts converging to the value. So I could also do Borel transforms and try to analyze put the same value of sigma and calculate the Borel resummations of all these instanton sectors, not instanton, sorry, non-hydrodynamic sectors. And I can see that the imaginary part, again, there's ambiguity cancellation guarantees that the imaginary part will be basically 0. And this is the attractor solution and the values that I'm calculating for the real part of F. And you can see, so of course there's still a divergence. I only included 2 instantons, 2 non-hydrodynamic modes, but the values of Z that I'm using are very small. So this is definitely not in the regime of late times anymore. So just quickly, I wanted to just mention the things that actually so this was a very, very simple example just to tell you what type of things we are actually using the asymptotic trans series, the resurgent trans series for. And in particular, for example, for the free energy of 2D gravity, we know that it obeys the Painlevé 1, nonlinear ODE, and we can actually study phase transitions basically what we want to study is the Lie-Young zeros of the partition function. So this is the free energy. We can calculate the partition function. And we want to, and these Lie-Young zeros are basically related to the poles of Paul-Levé. There's different solutions in the Paul-Levé one. So you have three different types. You have the tri-tronqué, where you have a whole set of poles in a small region. You have the tronqué, which has basically three of these regions with poles. And you have the general solution, which has poles everywhere. And what we want to do is exactly do the same type of analysis that I've mentioned just now, but in order to actually analytically determine the positions of the zeros of the partition function or the poles of Paul-Levé. You can even go further and do a similar thing to matrix models. Here we actually have a phase space because you have a 't Hooft moduli. So we want to analyze the large N expansion. This is the phase diagram. This is our Stokes regions where you have a large N expansion. This is an anti-Stokes region where you basically have that the exponentials are all of the same order. So it's an oscillatory behavior. And this is where you, for example, you'd expect the Lie-Young zeros to be, because that's where the partition function will have, like, it's like having sines and cosines, and you'll have zeros of sines and cosines from the exponentials. And basically doing the same thing, this is actually a very quick calculation of the zeros of this partition function, and you can see that the zeros will indeed already fall within this region where you would expect them to be. There's many open questions. Many gauge theories in matrix models. What happens with the other parameters when you vary them? So interpretation of some non-perturbative contributions. You might do an asymptotic analysis and then meaning find that you have non-perturbative phenomena, but you need to give a physical description of that non-perturbative phenomena, semi-classical description. Also, determining Stokes constants, it can be done numerically, but analytic descriptions of through integrable models or other ways of the Stokes constants are actually basically non-existent. And also, again, this part that I've spoken about here, which is the analytic properties of the asymptotic observables, try to analyze phase transitions, the role of initial conditions in our model, in our trans series, and also, for example, if you have boundaries and you have what's called matched asymptotics, this should be doable quite well with a trans series formalism. And this is just, well, thank you.
Questions? Questions?
One quick question. Very good. Basically, you showed that for this relativistic hydrodynamic plasma, you can understand the late time solutions and try to extract some properties of the mid-time solutions, and it got me thinking, so is this method also applicable in differential equations which have chaotic behavior, which have no stable, let's say, fixed points or stable cycles and so on? Would you be able to have resurgence appearing there?
So that seems that if you're in that situation, that you'd basically, well, from the physics point of view, you have no semi-classic understanding. So, and that means that basically you don't have any region of your of solving your ODE where you don't where you have a true perturbative expansion. So it would be, I don't know how we deal with analyzing asymptotics. Unless you have a region in your parameter space where you can actually solve the differential equation and have a perturbative approach there. So the answer is I don't know, but if you didn't, I couldn't see how you would be able to use this.
More questions? Okay, well, let's thank Ines again.
Sure.